Hello, everyone, and welcome to my presentation. The title of our paper is A Situation Our Adaptation Framework for Intelligent Transportation System. My name is Narit Islam, and my co author is Dr. Akramul Azim. And we're from Electrical Computer and Software Engineering Department of Ontario Tech University, Canada. So let's get started. Um, a transportation system is usually well defined and operates based on a specific model defined during system design. However, the system can interact with different objects from its environment at runtime and needs to guarantee its functional as well as timing behavior even in the presence of adverse or failure situations through self adaptations. So in this paper, actually, we present an adaptation framework which guarantees the functional and timing behavior of the system in different situations through creating a knowledge base from mining the video streams of the monitor system. So the knowledge base provides information of system information with external objects and constraints and characterizes the runtime behavior. So let's have a look what we mean by the environment of a real-time system or what basically contains an environmental a real-time transportation system. So apart from the set of tasks which is defined during design within a real-time transportation system, the system can also interact with different objects and even present in its environment. For example, a car in this scenario can interact, or its runtime behavior needs to address pedestrians walking in its environment, or and other vehicles walking in its environment, or maybe a change in the traffic signal. So that's what we propose. Our main view is that the system needs to have sufficient knowledge from its situations and their subsequent changes. Um, so let's look at some basic terminologies. So first comes objects. So what do you mean by an object is that any entity capable of movement or undergoing any changes in its state or behavior is called an object. For example, in the traffic example scenario, what we just looked at, the object can be entities such as car or pedestrians, which is present in the environment of the system. An event is a real world occurrences that can be expressed over time and space. So for example, the movement of a pedestrians from one side to another, or movement of a car from one side to another, or for a change of a traffic signal from red to green can be called as an event associated with some objects. And a situation can be defined as at a particular time tk. The situation is a collection of interactions among events present in the environment of the system. So, to characterize the operational environmental model, what we do, we take the video streams which is obtained from the environment of the system, and we use the video streams to identify and classify different objects using an existing machine learning based object detection methodology, which is called YOLO. Algorithm one actually details and explains what we do with object tracking. Basically, what we do, we track the object from video frame to video frame, and track and record what kind of changes they are going through. Such we use such changes associated with an object to characterize different events. So an event can be actually uttered as a real world occurrences associated with an object. So such identification actually allows us to characterize different situations in a particular time, using which we created a knowledge base which is called video mine. So the video mine allows us to analyze different events and their properties. So using which we can identify different events such as basic events as well as derived events. So derived events are those events which is actually obtained from basic events. It also allows us to analyze the system overload as well as the performance analysis of the system safety. Formation of video mine actually includes identifying For each identified events, we determine if it's a newly arrived event or if it's an existing event which is already in the system. So for an existing system, we determine its type and properties such as periodicity, duration, time of arrival, etc. We also use the basic events to identify derived events defined in equation 6, 7, and 8 of the paper. If the derived event is a newly arrived event or aperiodic, we store its properties in the video mine. However, if it's a periodic event, we avoid storing it because it's first occurrence and periodicity is already stored. We also avoid storing the basic events because the corresponding detected events are already stored. So let's look at our our adaptation framework itself. So basically, we have two modes of operation. One is basic mode, and another is adaptive mode. So in basic mode, basically the system actually executes the its internal tasks, and actually it schedules them on the processor defined by any scheduling algorithm which is characterized by the scheduler. However, we allow the system to run into adaptive mode as well. So, in adaptive mode, the system takes the environmental situations into account, and for each event in a particular situation, it maps them to a set of tasks. And before characterizing and scheduling those tasks into the processors, what we do, we perform an early verification. Basically, we we actually use a set of constraints, and using them we actually check the properties of the task to see if it will cause any failure or any drastic or carrying any catastrophic consequences. If it is passes the verification, we actually add with the internal task and allow it to run in the processor. So our main experimental analysis consists of two case studies. One is a driver assistance system and another is a real-time traffic monitoring system. In both cases, we actually have a camera placed on top of the system which monitors the environment of the system. And we run following experimental analysis, which are comparison between traditional video comparison methods, identification of properties of the events. We also verify the correctness of the requirements, which generates the task. We also analyze scheduling overhead and use them to compare different performance of different scheduling algorithms with our approach. We also perform comparative failure analysis as well as an analysis on the response time due to adoption. So when we form a knowledge base in case study one, we had 17,234 events, out of which 16,993 were basic and 241 was derived. In case study two, we had total 9,404 events, out of which 9,223 were basic and 181 was derived from the basic. So when you looked at analyzing scheduling overhead, so we actually perform a comparison of scheduler complexity with our proposed method. So basically, what happens in this case is that in our early verification steps, we reject a number of unnecessary tasks, which uh, doesn't need to be executed or um, which may cause some sort of failure to the system because they fail to meet some timing constraints. So which is why actually we experience a significant amount of reduction in terms of scheduling overload. We also perform a comparative failure analysis. For the comparative failure analysis, we perform both component and event based safety analysis. And as we reject the tasks which is likely to cause failure, since they are rejected, so the performance analysis in this case, because of the early evaluation, in this case is significantly low in comparisons to the task if they are not considered without the evaluation. So for the failure analysis, basically what we do, we use seal along with a fault tree for each situation to identify the probability of a failure of probability of failure of the system at that particular time. We also perform an analysis of the response time, which is due to adaptation. So basically, we use video mine to store the different situations, and we also use video mine to map the tasks which is associated with different events of a situation. So, for example, later on when we encounter same situation, the mapping is significantly low, or the mapping time is significantly low because they are already stored. So what happens here is that we have an like optimized mapping which combines with the early verification process, and as a result the adaptation framework results in a very reduced response time. So in this paper, basically, we present a situation our adaptation framework which changed the behavior of the transportation system to accommodate new tasks in different situations and guarantee functional as well as timing behavior throughout the system. So we monitored the environmental situations and identify different real world occurrences. We also identify the relationships among the events and identify basic and derived events. And thereby we create a knowledge base which is called video mine, which allows faster information retrieval and onboard storage, which is ideally suitable for our transportation system. Um, the adaptation framework also facilitates adaptation by identifying the adaptive tasks needed to be activated in response to the current situations. We also evaluate the task based on different timing constraints, and the adaptation framework actually ensures the functional as well as timing requirement. And we have looked at that it also improves the overall responsible times and scheduling overload. Thank you.